Good morning, comrade subscribers. For this video, I want to go back to my roots, so to speak. I did have a Commodore VIC-20 growing up. I did have a mate at school that did have one. But I kind of like the VIC-20. It's got a great keyboard, and it's kind of a bit of an underdog with, small amount of RAM it's got. So I did quite a few videos on it when I first started out, and I thought we'd come back to it. So I was talking to, having an interesting discussion with Gary and Matthew on my Patreon. Should check it out. And one of the things I wanted to do back when I was doing VIC-20 videos, and I should come back to doing this, I've been busy with other things, is replacing the internal RAM with just a 62 with an 8K 6264. So I don't think the way it's a bit weird in the VIC-20. The memory is organised in blocks of 8K. So we're just talking about block 0 here at the moment, which we can see down here. So I'm just talking about the original 9-volt VIC-20s. I don't know about the later ones. But the RAM's comprised of these 2114 chips, which are basically half a K each, so 1024 by 4-bit nibbles. So 2 chips make up 1K. So we've got 1K, 2K, 3K, 4K, 5K, 5.5K. This extra half K is the actual color RAM, which is, we won't worry about that for now. We'll just look at this 4K here. And we've got 1K, which is right at the start of RAM, of the memory map, 0 page that's used by the system for the heap and things like that. And then we've got 4K, I think that's actually usable by the user. I think it turns out to be 3.5K or something at the end of the day. But there is a 3 kilobyte hole in that first block. So we've got 1K, then we've got a 3K gap squeezed in there, and then we've got the remaining 4K. So if we do an 8K expansion, that'll fill in that 3K hole there. So we'll have basically 8K. So the way they did it originally was with these sort of cartridges, the 3K RAM cartridge. So this is the 3K RAM cartridge with super expander. So that'll fill in that 3K hole and give you some extra commands as well. So why do we want to do this? Well, just in case if you've got a RAM fault, rather than trying to source an original 2114, you can just stick in a 6264 and recover all those chips. Some might still be working. And also to reduce heat, one of my early videos, I was obsessed with reducing the power draw of the VIC-20. So you reduce the heat, for example, replacing chips with CMOS versions. So replacing these will reduce power as well. And there was a third reason. Oh, well, you've got a VIC-20 that's by default now 8K machine rather than a 5K machine. So I thought it might be interesting to do a KiCad video on it, because it's not just a case of just pulling these out, putting in the 6264 and you're done. Because like I said, the memory maps is a bit weird, so we need to sort out the decoding of the various select lines and things like that. So there's a little bit of work involved in it. And we'll probably use grok. Grok's been quite handy in explaining how things work and giving me ideas on how to do stuff. So we'll probably involve grok as well in the design. So that's the reasons behind it. Let's go and start. Let's start. How shall we do this? Well, this is the memory map of the VIC-20. Have a closer look. So we can see it's split up into blocks. So the red parts are what's in the unexpanded VIC. So we've got 1K, then we've got the 3K gap, then we've got 4K there, so that makes up the 8K of block 0. Then we've got block 1, block 2, block 3, Got the character ROM there at 8000. Got block 5, basic and kernel ROMs up there. So the 3K here you can see is RAM 1, 2 and 3. So that's what the selectors are for them. So here we go. So block 0 is what we're interested in. Basically filling in this 3K. Well, we're replacing the existing 5K and also filling in this 3K. But at the same time, it would be good to have it selectable so that we've got a switch so that we can switch this 3K off and on. So we can go between unexpanded and 3K expanded VIC. And as you can see here, if this block 0 works, then we could probably quite simply, famous last words, extend it by adding some extra 8K blocks and increase the internal RAM even further. So yeah, that's what we need to do. How are we going to do it? So let's have a look. I've got the schematic open somewhere. Okay, so here's the schematic. As you can see, we've got the 2114, so that makes up a kibby nibble each. So 2 of these make up one kilobyte or 1 kibby byte if we want to be pedantic. So we've got 1K, 2K, 3K, 4K and 5K. Obviously this is the lower K, this is, start of memory there, the 0 chip select. Up here we've got a kibby nibble by itself, so this is the color RAM. So we're not worried about this at the moment, this is kind of out of scope. But I guess it would be good to replace that as well, in case that is faulty. But if we're going to recover all of these, then, hopefully one of them works that we can stick in there. Anyway, so the chip select, that's going to be the major one. So you can see here we've got the chip selects are tied together for each 1K section of memory. And they come out of this 74LS138, this 3 to 8 decoder. And so we've got these 3 signals off here. If we follow them down, we can see they are the RAM 1, 2 and 3. So these 3 signals are for the missing 3K block that we need to fill in. And then we've got continuing on 4, 5, 6, 7 for the remaining sections of memory, 1K blocks of memory. I'm trying to avoid saying block. So block as in an 8K block or a 1K block. So what we essentially want to do, we're replacing all of these 8 chips with our single chip. We've got address A0 to A9 on here, so we can recover the address from one of these chip locations, and then we've got 4 bits and 4 bits on the data bus, so we can reuse those as well. The idea is that we've removed these chips. Now, chip select. Obviously, we've got all these chip selects here. We need to basically tie them all into one chip select for our one chip. Although actually, if we have a look at the data sheet, there's actually 2 chip selects. We've got a active low and we've got an active high, which isn't a problem. We just need to generate some chip select signal and then invert it for the other one. So you can see here, we basically need both of them by the looks of it. So we can't tie one, or we can't tie one to ground, or we can't leave it floating. But it's not a problem. Like I said, we generate chip select 1 and then we just invert it to get chip select 2. So that's not a problem there. So what do we need to do? Well, basically we need to kind of reproduce this logic here. So what have we got? So we've got A10, A11 and A12 address lines coming in. So they are the ones that are basically selecting which part of the 8K block of RAM, 1K, 2K, 3K, etc. Then we've got A13 address coming in on the enable line. So we've got 2 enable lines. We've got one that's active high and one that's active low. So A13 is active high, so that means when it's high, we're selecting this. So let's have a look. So it comes out of there, okay, it comes out of a buffer, I guess from that, but let's have a look where else it goes off somewhere else. Follow it up. Okay, it goes into this ROM, into this, what is it, 4K ROM, address 8000. So I think that was the character. I think that was the character ROM. 8000, yeah, that's the character ROM, which is chip select for where was there? Chip select for the character ROM. So that basically means that it needs to be active low. So if A13 is low, we're selecting the character ROM. If it's high, we're selecting the RAM. So that kind of makes sense. Now for this one here, this is active low. So G2A, where does that come from? That comes from this NOR gate, which comes from here. Okay, so it comes from this 74LS138. So it looks like blocks. So it looks like this is the block selector, I guess. So block 0, which makes sense. Then we invert it. Then we NOR it with this S01, which has come out of the CPU. Okay, I'm not too worried about how it's calculated. We just need to know that it's active low. So it looks like for a start we need A13 to be high, and I guess block zero signal to be low. And if we're active low, that means we want this to generate a low output. So let's make a note of that. What did I say? So we've got VA, so this is 6264 RAM, chip select. So we've got VA13, that needs to be high. And then we've got block 0, that needs to be low. So the result of that, how can I draw this? So the result of that is low. We want low. So the table for that would be, if we go A, B, C. So let's just fill this in low, 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 high, high, low, high, high, high. So we want it low. We want it low only for high, low. Everything else we want it high. Okay. So that's the logic table basically for that. But also, if we want to be able to switch off the expansion, we need to take into account A10 to A12. So if we have the expansion switched off, so say we use a switch, just a single pole switch. If we have it switched on, well, it doesn't matter, on or off, whichever way. If we have it switched on, for example, we want the full 8K. So we want all of these to be available, the whole 8K. If we switch it off, we'll switch it the other way, then we want it to go back to the original unexpanded. So in that case, these three are ignored, basically. We only have the original 5K that we're accessing, if that makes sense. Maybe it's a bit too much, but at least this way we don't have to worry about with any possible software incompatibilities. If something is expected to run on an unexpanded VIC, we don't want the memory to be kind of, the memory map to be a bit weird or whatever. So to do that, where is my other notes here? Here we go. So this is block 0. So we've got the first 1K. Here we can see that A12, A11 and A10 are all 0. So when they're all 0, that's block 1. That's okay. For the upper 4K, we can see that A12 is always active, so we want A12 and then basically A10 or A11. So for the 3K expansion, A12 is always low, and A10 or A11. I'm just trying to think of how I did. I did some work on this yesterday. It's unexpanded VIC, so active only for A12 is low, A11 is low. Whoops. A12 is low, A11 is low, A10 is low, or A12 is high. Yep. Okay. That's what we want. That'll cover that 4K and that 1K, that condition. So I think this is probably the condition that we want to match. So we have a switch. So when the switch is on, for example, we only activate the chip select for those address lines. Otherwise, if we have it switched off, then we don't care what the address lines are. If that makes sense. That's basically how we need to design it, I think. So that's basically it. So now I think we can get grok to help us figure out how to do it. I want to just use a GAL. I think a GAL, have the RAM chip and the GAL. I think that's the easiest way to do it. That way, because you can reprogram the GAL. If you make a mistake with the logic, rather than using discrete logic, if we just design it with a GAL, that way we can just reprogram the GAL. So let's ask grok to help us with that now. All right, grok. All right, how shall we phrase this? I am designing an internal 8KB RAM expansion for the Commodore VIC-20. It will use a 6264 RAM chip. Okay, to place the internal, block 0 RAM. The 6264 chip select, active low. We'll just give it active low. I know it's both, but get it to calculate for active low, and then we just need to invert whatever to get the active high. The chip select for active, the chip select should only be active. No, we need to tell it the signals. There will be these input signals. Okay, for the chip select. So we've got VA10, VA11, VA12, VA13 and block 0. So the chip select should only be active when, let's say VA13 is high, I think it was, wasn't it? VA13 is high. Let's have a look. When VA13 is high and block 0 is low. It is high and block 0 is low. And now we want to talk about the switch. Additionally, we could probably build this up, but I think try and do it all at once. Let's see. Additionally, there will be a switch to decide or to determine whether the full 8KB is active or only a section. Okay. if the switch is on, okay, if the switch is on, then all, no, let's just go the other way. If the switch is off, no, so additionally there will be a switch to determine whether the full 8K is active or only a section which is determined by VA10, VA11, VA12. If the switch is on, then all addresses are handled, maybe, regardless of VA10, VA11, VA12 value. If the switch is off, then only then the following conditions need to be met. So we want, what was it? I think it was down here. So A12 is high, VA12 is high, or A12, A10, so basically all of them are low, or VA10, VA11, VA12 are low. So if the switch is on, then all addresses are handled, so that means the full 8K. If the switch is off, then the following conditions are met. Then if the following conditions are met, if the switch is off, then if the following, then the following conditions should be met. Yeah. Switches off, the following conditions should be met. Okay, if the switch is off, then I should say then the chip select will only be active if the following conditions are met. I think that covers everything. So we told it what sort of computer we've got, what the RAM, so it knows the pinout. There will be these input signals, so we've told them the input signals. So the overall chip select should only be active when VA13 is high and block 0 is low. Additionally, if we use a switch, so if the switch is on, then we handle everything. All handles are regardless, okay, but dependent on the chip select. If the switch is off, then the chip select will only be active if the following conditions are met. Okay, let's see what happens. Okay, so basic chip selection conditions. Chip select is active when high-low, yep. Switch behavior. Switch is on, the full 8K, meaning chip select is active regardless of these address values as long as the basic conditions are met. Correct. Switch off. CS is only active if the basic conditions are met. Correct. And one of the following conditions. So VA12 is high or VA are all low. Correct. This has a chip select active low pin 20, right enable. Output, okay, right, yep, we're designing logic for CS based on those. Right, okay. Let's denote the switch state as SW, okay. The chip select can be expressed as a Boolean. So basic chip select, so chip select is, this can be written as, so basic chip select is, okay, so VA13 high and not, okay, so high and high, yep, correct. Since CS is active low, we need to invert that. Okay. So again, we've got two chip selects, so we could either use that and then invert it for the. We'll sort it out because we're going to use a gal anyway. So we invert that, which ends up being that. However, this is only part of the logic, as we need to incorporate the switch and address conditions. Okay. So the address condition is basically VA12. Yep. So the upper 4K or the lower 1K. Switch on condition. So when the switch is on, we ignore those. We're ignoring them for the chip select. We're not actually ignoring them for the actual data handling because we are still going to have those addresses coming in, but we're just ignoring them for this. Okay, and chip select is active as long as the basic condition is met, correct. So now this is right, getting a bit confusing, yep. So then we invert it again, simplify the logic, so this is where this comes in handy. Okay, to implement this you can use standard, so 74LS. So we use some inverters, some AND gates, some NAND gates, some OR gates. So here we go explaining how to, so we use a 3-input AND gate. Okay, blah, 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 blah. All right, so now we want to use a gal. This is excellent. Here we go. Address space. Oh, here we go. So to verify the design, let's map the address space. Okay, so block 0. Block 0 corresponds to that, 1 kilobyte, but we're expanding to 8 kilobytes, correct. So A13, this corresponds to addresses where A13 equals 1, i.e. 2000 above. These correspond to defining 8K blocks within block 0. Okay. So when switch equals 1, the entire 8K is mapped as long as A13 is high. Yes, because it's active low for the actual character ROM selection. And block 0 is low because, again, this chip select is active low. When switch is 0, the chip select is only active for the top 4K of block 0 and the bottom 1K. This effectively maps that, correct. So total 5K active when switch is off, which aligns with the partial RAM enablement. Perfect. Okay, so switch implementation, decoupling, yep, always going to do, yep, we'll add decoupling. Unused pins, so tie unused pins, well, we need to connect them. Yep, so we'll connect them all. Phi 2 for, okay, we'll have a look at that. Okay. All right. Okay, time to use NAND gates for a compact implementation. Well, we want to use a gal, so let's go. Can this be implemented using a gal? Yes. Okay. A gal 16V8. Yeah, I've got some of those. All right. Here we go. Programming the gal. Okay, this is more than what we need at the moment. And this is just telling us what about connecting it all up. There we go. So this is the final gal. Too easy. So this is our little gal program. About pin 15, but we can change all this. So I think can we well, let's just copy this. All right, so because what we actually need So we'll put this on one line. Oh, okay, so let's have a look. I think I've got where's the, here we go. Okay, so so the inputs are pin 2 to pin 9. So input 2, 3, 4, 5, 6, 7, right? And then we've got the outputs from pin 12. So we're choosing pin 15. And maybe it depends. We could maybe go up to pin 19, couldn't we? Depending on how okay, let's just do it like that. So let's add, this is the active, that's active low, isn't it? Because it's generating the active low. Pin 16 is, and then we invert it, and we get the active high, which is CS2. Active low, CS1. So that basically should be it for our gal. So A13 is low, or what did it say? Or, okay, because this is okay, that's inverted. Or, okay, I will have a read through all of this. Okay, so the gal will configure the output CS as active low by default, which is what we want. Okay. So let's just have a look at the logic. Oof, jeez. Okay. So clock 1, so tight to ground, okay. All right. Other pins not used, tie to ground or leave unconnected. Okay. For the logic, we need that. Yep. Okay. So the chip select logic is, so that's the chip select logic. So starting with that, and then we're, I guess, separating. I'm not familiar with De Morgan's theorem. It's been quite a few decades since I went to uni, so I guess we're simplifying. All right, so the main thing is, like with the gal, is that if it's not working, we can hopefully reprogram it. All right. So we've got the basics. Let's finally see if we can start designing something up. Let's do a schematic. So I think the schematic's going to be pretty simple. Let's get some parts. So 64, 62, 64. So just the RAM chip. So we'll stick the RAM chip in. Just rename that like so. Let's stick the gal in. So what was it? The gal. There we go. 16V8. Let's stick that in. Okay. I think that's basically the only two chips we need on the daughter board. Now the idea is, let's have a look. I've got a picture. Okay, so this is the 74LS138 where we're going to be picking up some of the signals from, and this here is the 5K that we're replacing. This one here, this is the color RAM, so we're not worried about that at the moment. So I figured we would remove all of these 8 chips, and then here we would stick a pair of sockets that the daughter board can plug into. That way we'll get access to those address signals and also the data bus. And also power and ground. So actually, let's just do power and ground while we're here. So, well, actually, let's do the. So these are what? I think these are 18 pin. Okay, they're 18 pins. So for those, we just can use connectors. So if we have a look for, do a search for the connectors, connector, and we want, I don't know if this, no, we want 2 rows, don't we? 2 rows by 9. Yeah, counterclockwise, perfect. So this kind of replicates a chip. Pins 1 to 9, then we go 10 to 18. So we can use this to represent our get another one of those to represent our 2 RAM chips that we're removing. So UD4 and UE4. So let's call that one UD4 and UE4, like so. And then we just need some other connectors. So we need the switch. All right, so we need a connector for the switch. That's pretty easy. That's a 1x02. I prefer them when they look like that. So that'll be our switch to enable or disable the 3K expansion. And then we just need those additional signals. Have a look at the schematic. So we need A10, A11, A12, A13, and then block 0. So we just need 5 signals because we're getting power and ground through the RAM chips. So let's get another connector, a 1x5, like so. I know we could just have a 1x7, but I prefer this way. We can handle these separately. We can put them on different sides of the board or whatever. I think that's essentially what we need. Oh, and decoupling. We need some decoupling. We'll do a decoupling capacitor for each of these. And I think that is basically it. What am I looking for? Capacitor. I just have a mental device. Okay, I just had a mental break. 1, 2. Just the standard 100 nanofarads or 0.1 microfarads, whatever you want. Okay, so let's sort out power and ground first. So power and ground we're getting from these chips here. So ground is pin 9 and power is pin 18. So let's just have ground and power. Pin 9. Alright, and let's duplicate that. Stick one over here. And we need that on the chips as well. And I think we'll need it on the switch. I think we'll need one on the switch. So let's just stick that there for now. And then 5 volts. So let's just add in another label, plus 5 volts. That's on pin 18. Let's copy that, stick that there. Stick another one over here. Stick one on the switch as well. We'll have it at pull up, so I'll need a resistor. Stick it here on the chips. And that should be it. So let's finish off the decoupling capacitors. Let's just connect them up. And then connect them to power. Okay, and let's just move them. Well, let's just move them over here for now. Okay. Now the switch. Well, let's do the inputs. Okay, so that's the switch. So this will be I don't know, signals or something. So we've got VA 10, 11, 12, 13, and block 0. I think I was going to call them. So let's just call them the same thing. Let's do that. Okay, VA 11, VA 12, VA 13. Oh, it's VA 13 slash G1. So okay, that would be, make it nice and clear. And this was block 0 slash G2A. Like that. So we're getting those signals in from the 74LS138. They need to go into the GAL as per our little program. Where was our little program? Here we go. So pin 2, 3, 4, 5, 6, 7. All right, like that. So same order, and then switch is pin 7. All right. So pin 2. So we basically want these over there. So let's copy them, paste them, and connect them up like so. And then pin 7 was this switch here. Okay, let's call that switch then. Now, okay, so the way it's going to work, I think, with the switch is when it's off, let's add a resistor in, pull up resistor. That's not a resistor. Okay. Let's stick that like that. Okay. So the idea is, now the thing is, you're going to have to make sure you've got the switch around the right way when you plug it in. So if we connect the switch, maybe I should just call it S. I wonder if that's going to confuse things. Let's just call it S. I was going to call it unexpanded or unexp or something, but that's too long. Let's just call it S. Okay. So the idea here is if the switch is open, then S is connected, is pulled up high, is pulled high. S is pulled high. When the switch is closed, then S is pulled low. That's the idea there. Does that make sense? And then, I don't know, I normally put 10K, but you could probably put 1K or 2K or whatever. I just do 10K because that's what I've seen other people do. Okay. There we go. So we're getting somewhere. Now for the outputs, pin 15 and pin 16. So we've got pin 15 and 16. So pin 15 is CS1, I think, because I said active low. So pin 15 should be CS1. So let's call that CS1 then. CS1, active low. So on pin 15. And also on pin 20. And then let's invert it. Well, let's take the inverted from pin 16 and feed it into there.
Now we've got output enable as well, so I assume probably have to tie that to CS1, probably, but we'll look at that in a minute. Now for the gal, let's, what is it? What did it tell me about the gal? We could probably read it from the I don't know what Ultra Editor's doing these days. It keeps splitting windows on me. Really driving me insane. I don't know why is it doing this? Oh, doing my head in. That's my start of my Sargon for the Radio 86. Anyway, let's have a look down at our questions for the gal. Okay. Tie pin 1 to ground or VCC. Okay. So let's just tie that to VCC. Like so. What about unused outputs? Okay, pin 20 to 5 volts, pin 10 to ground. Yep. Add a 0.1 decoupling. Yeah, okay. Connect those to the assigned inputs. For switch, use a toggle with the pull-up. Okay, well, I've already done that. Oh, 10K to 5. Well, that's what I've done, yeah. Connect pin 15. Yep, okay. Leave unused I/O pins unconnected or tie them to ground in the programmer software. Okay, so to avoid floating inputs. So I'll have to set them to ground then in the I'll have to look into that. So normally I would just have them disconnected like that. But we don't want them floating. What does it say about the output enable? We tie it to ground, I think. 12 to 14. Unconnected. Oh, okay. 12 to 14 and 16 to 19. Okay, yeah, so we definitely leave those disconnected. And pins 8 and 9. I'll worry about all the tidying up at the end. I won't sit here going through it all. Just I thought it said something about the output enable. Okay, disable the clock pin by tying it to ground or VCC. Program the gal. Ensure the gal is set up to simple mode. Okay, for pin 15. Okay, and 16. I'm assuming the output enable. I probably need to tie that to ground. Okay, we'll worry about that later. Now, address lines. So we've got A0 to A12, so this is pretty easy. Let's go A0, like so, and then we just go F1, fill in the rest, like so. Although, I can call it VA, didn't it? Actually, it's VA. I better call it VA. That's easy, easily fixed. Let's do that again. VA0. So there. And then that way VA10, we're picking up VA10, VA11, VA12 from there. Right, so for VA0 to VA9, we just need, they're the same on both, so we just need to pick them up from one of these chips. I think I have the data sheet here. A012, so 567. 567. 5. And then I can go, whoops, 567. And then I've got to go up to backwards 3, 4, 5, 6. Okay, 3, 4, 5, 6. VA3. I don't think I can go, but it only goes downwards, so we'll have to. And was it? Yeah, it was like that, wasn't it? Yeah. VA4. VA5. VA6. And then A6, A7, A8, A9. Okay, 17, 16, 15. I can do those. What was it? VA7. I think it was 17, wasn't it? Yep. And then I can do my shortcut finally again. Alright, so we've got A0 to A9, and we've got A10 to A12. Alright, what's pin 8? Chip select. We don't care about that. We don't care about that. And yeah, we don't need to worry about these ones because we've already got the address lines coming in. Okay, now we've got the we've got write enable. Write enable. Oh yes, that's what we need. Write enable. What do we call it on the schematic? VRW. Okay, so let's call that VRW. VRW. That's pin 10. Okay. Let's just move this a little bit. There we go. Okay. Now, looking at it, so this is the lower half of the byte, BD0 to BD3. BD0 to BD3, I believe. I think that's the way I checked it. I'll fix it up in the final wash. So say that is BD0 to BD3. Sorry, what pins are they actually? Data sheet. Oh, okay. Too easy. And again, F1. Done. Now similarly over here, so we've got BD4. Five, 6, 7. And then that's not connected. Okay. So we've got our addresses coming in, we've got our data going out. We've got our addresses coming in, now we just need to do our data going out here. So BD0, there, and then done. That's just about done. I just need to double check a few of these connections. Output enable, let's have a look at the data sheet again. So I think we need to tie output enable, so it needs to be low or okay, so it needs to be low for a read and it can be low or high for a write, doesn't matter. So let's tie it to CS1 basically. Oh no, hang on. Oh, it doesn't matter anyway if that's high. Low, high, low. Write enable. All right, let me have a little think about this logic here. Output is disabled. Ooh, to do we want? Because we don't have that on the... I'm thinking we just tie it to chip select 1. Anyway, I think that's all basically done, isn't it? Let me just finish off these few extra little bits here with whatever, and then it'll be time to do footprints. It's the final schematic. So I asked Grok, what should I do about the output enable pin? And it actually gave me quite a complex answer. Basically tying in, because it remembered the previous discussion. Now I'm talking about the Commodore VIC-20, and it actually told me. So I've added 2 new inputs to the GAL, and added another equation. The output enable basically should be this. So I've added another output pin for the output enable. Excuse me. And I'm bringing in additionally the read write, and which I already had coming in from the other RAM chips, and Phi2 from the 6502, which you can actually see kind of here. Here's Phi2 going into this NOR gate, and then we pick it off. I don't know where this SO2 goes over here, and so according to Grok, the most for RAM expansions, apparently it's most commonly we take Phi2 and NAND it, I think, with whatever I'm doing with the read write. So, I'll include all this. Will all be on the GitHub. It's including all of Grok's analysis. So it's in-depth reading there. But yeah, that's the final schematic. And I've tied the output enable of the GAL active low. I've tied it to ground, so it's always active as well. I changed this to a 6-pin input. There we go. So let's now assign footprints. Okay, so let's start with the capacitors. So capacitor through hole. There's going to be ceramic, so C disc, say pitch 2.5, small ones. What have I got? So maybe those ones there. So that's them done. These two will just be, they'll just be like single inline pins. I'm not actually going to have a socket or anything for these. These are going to be pins so that I can plug into a socket on the motherboard. So they will be connector pin. Oh, what should I put them as? No, I do it as. Can I do it as? I don't know if this one allows you to do a row of 2. I think this is just plain pin headers, yeah. So let's just do that as a package dip. So they are 18 pins. So we'll do dip 18, and they're, I think, 300 mil wide. I think that's the one we want, isn't it? I think, or we could do socket. Doesn't really. Well, let's just do that one. Okay, switch, that's just going to be a connector. Those, well, both of them are going to be connectors. So connector, pin header 2.5. So we want a 1x02 for that one. Vertical. And that one is a 6-pin. Vertical. Now the resistor, I should note down which one I end up doing. So it's axial, and I say I think they're generally 6.3 mil, and horizontal 7.62. I think that's enough space. Okay. I might and then we've got two packages again. Package dip. What's the gal? The gal is a 20 pin. Dip 20. And it's a narrow one. It'll be a socket actually. I'm going to socket it. And we'll change this one. This is the RAM chip. We'll change that one to a socket as well, shall we? Socket. Like that. And that should be it. Let's see. So now the dimensions of the PCB are going to depend on these two. If we have a look at our picture. So if we're going to plug it into here, we want these two pins up here. We need to, I've already measured them, that's 30 mil. 30 mil. So that's 30 mil between them. So as long as they're both in line and pin one is 30 mil apart, the other two can be whatever. That's that should be basically how we go. So update PCB from schematic. Okay. Here is everything. So where are... Okay, these are our two... Okay. So UD4, I think, goes above. And then this one goes underneath it. So one quick way to do it is if we make pin 1, and we've got 1 mil, okay, 1 mil grid. So pin 1 is the origin. So that means that this one should be 0x offset and 30 mil y offset. Okay, so that's it. That's it. That's kind of our limitations. So now it's just a case of moving these around. Okay, so what have we got here? So we've got the decoupling caps. We've got, there we go. Let's move this one. Well, they're not connected to anything, but one of them goes, let's go C2 and U2, and then C1 and U1, like so. And then we've got the switch and its pull up resistor. So we want them kind of close to, because this switch gives an input to the GAL. As we can see there, we've got a switch input. Rotate that around, like so. We can rotate that around. Just trying to minimize paths. And then that's basically it. So, and then, you know, we could, if we wanted to, just like this, we were just sloppily doing it. Edge cuts, and then just draw a box around it. And then very quickly just do a ground plane as well on the bottom half, like so, and then do auto routing. I'm just not saying this is how I'm going to leave it. I'm just saying if you wanted to do it, that's basically it. That's done. And then we go fill all zones, and that's it. It's done. Off to fabrication. But obviously what I want to do is try and minimize these paths and get things to line up. Like for example over here with these, I could move these down so that they're in line with their inputs. Anyway, so I'll work around, fiddle around with this, and I should be back hopefully with the finalized design. Here's the final result. So Just checking. I'm pretty sure there's no isolated ground islands, and I think everything's been routed. There's nothing. We can do a quick design rule checker. Okay. All right. Nothing obvious there. What doesn't it like there? What was this one? Text thickness out of range. Okay, won't worry about that. So there we go. Now, thanks to PCBWay, let's just save that. Yeah, I think let's have a quick look at the 3D. There we go. So plug in the GAL, plug in the RAM. Now these won't actually be chips. These will just be a row of pins that we use to plug into the motherboard of the VIC-20 to pick up the address signals and the data bus signals. And the other ones that we can't get through there, we'll just have some wires coming off, some fly leads, for example. So what do you think? Worth a try? Let's go back. So thanks to PCBWay, awesome channel sponsor. So there we go. We've generated the Gerber files, Gerber, however you pronounce it. And we can also go, whoops, sorry, where am I? What am I doing? That's Finder, that's why. We can also use the plugin for KiCad and upload it straight to the website. There we go. So $5 for 5 boards. I don't think I need any more because I don't know if it's going to work. So it's just an experimental. Oh, I can get 10 boards. It's the same price. Who knows, it might work. Should we get green, or should we, if we get different colours, it adds a few days. Let's just stick with green. And yep, global direct shipping, $5. So $10 for 10 PCBs. Thank you very much, PCBWay. And yeah, probably about 2 weeks, or just under 2 weeks. That's the image I used. Just under 2 weeks, we'll have it back and see if it works. I guess, yeah. Okay. As always, I'm more than happy to get constructive feedback. What mistakes have I made? What assumptions have I made that are invalid? So please do let me know. Thank you very much. Bye for now.